Hello everyone. This tutorial is a series of video about integrated simulation, including reservoir simulation, well simulation, and production network simulation. For reservoir simulation, we will use software MBAL, and then for the well simulation, we will use Prosper, and then we will integrate the results from MBAL and Prosper to network simulation using GAP. All right. And in this video, we will focus only on the reservoir part using MBAL software. Okay. So we are now inside the MBAL. As you can see, we have file, tool, units, and help. All right. You can open units first and you can select the preferred unit that you will use in your calculation in your day-to-day work. Okay. All right. You can arrange everything now before the job, before the simulation, or you can change the units later on. Okay. So I just want to show you the units. Okay. I will not change anything now. So I click OK. Now we go to tool and you can see several features, several tools, and we want to use material balance. Okay. Again, you can check the units if you want. If not, click OK. All right. So our case today is about gas reservoir. All right. It will produce gas and the gas will be produced with 4 wells. All right. Later on, we will simulate the well using Prosper software, and then it will connect to the network. And finally, it will end in separator. And we will do that in GAP. Okay. Now we will create the reservoir model first. Okay. So we click options. You can follow me, the reservoir fluid gas. Okay. And then tank model single tank, no abnormal pressure, production history by tank, and no compositional model or simulation. Okay. If you have informations like company, field, location, platform, analyst, and any comment, you can put them here. Click OK or click Done. And then we go to PVT, fluid properties. Okay. And as you can see, we need to put several fluid properties data. And now I have my data. You can follow me for gas gravity 0.77, separator pressure, all right, at this pressure in PSIG. So you can see the units, the selected units. If you don't want to use these units, you can change the units again here. Okay, so for condensate to gas ratio, this number with condensate gravity of 63 degrees API, water salinity 100,000 ppm, no hydrogen sulfate, but we have carbon dioxide of 0.37 in percent and nitrogen of 4%. Okay, it is better if we match this the laboratory data with correlation. So later on we can use the best correlation that matched our data. Okay, suppose we have and we must have the laboratory data. Click match and I do the laboratory job in the reservoir temperature 166 degrees Fahrenheit, but I only have 2 points. Unfortunately, I only have 2 points during my laboratory analysis. And the pressure is this one, quite detailed, 0.3. And the second one is at this pressure. And then I measure, I calculate, or I analyze the Z factor 0.906. And for the second pressure, this one. With the gas formation volume factor in cubic feet per standard cubic feet, this number, or quite detailed, right? And this one. Okay. Lastly, for the gas viscosity, all right. Okay, let's say I have 2 points. Okay, and then I want to match it with correlations. Okay, click match. You can see for gas viscosity, we only have Lee et al. Or Carr et al. All right. And the matching is quite easy. You can just click calc and make sure you tick this one, match all. And yeah, there you have the correlation or the matching. First, for Lee et al., we check the standard deviation, the parameter 1 and parameter 2, and you can also check for Carr et al. Okay. Or you can also click this one, match parameters, to see all the numbers. And of course, we can select the best parameter based on what? Based on these parameters. There are at least 2 ways or 3 ways to see which is the best correlation. The first one is by standard deviation. All right. The best selection usually has the lowest or the smallest standard deviation. And between Lee et al. And Carr et al., you can see the standard deviation that is smallest is from Lee et al. You can see e to the power of -8, and here we have -7. So standard deviation in Lee et al. Is smaller than Carr et al. And for parameter 1, we prefer the number that is closest to unity or to 1. And here we have 1.07, but in Carr et al. We have 1.6. So the closest to 1 is actually Lee et al., which is 1.07. And for parameter 2, we prefer the number that is closest to 0. Okay? If parameter 1, we prefer closest to 1, but parameter 2, we prefer closest to 0. Okay, you can see the guidance if you can read or if you read the help. Okay, so the closest one to 0 is actually from Lee et al. Okay, all right. This one is very small, e to the power of -5, but it is bigger. Okay, and then yeah, you can check for Z factor and also gas formation volume factor. Okay, for gas viscosity, you can compare between Lee et al. And Carr et al. But for Z factor and gas formation volume factor, we only have one option. You can see these numbers for Lee et al. But if I change it to Carr et al., no change for Z factor and gas formation volume factor. Okay, so we just want to, or we can only have, or we can do on selection only for gas viscosity. And for gas viscosity, the best one is Lee et al. All right. Okay, so now we can plot, click plot, and then, or I can do the plotting later, click done, click here, or match all. Okay, I click calc again. Okay, so click plot, and you can see we can plot Lee et al. Correlation, Carr et al. Correlation, and also the laboratory data, or here written in match data. Okay, click here or click the match data first. We have data for gas viscosity, only 2 points. That's why we have line here, only 2 points, the point 1 and point 2. And what about Lee et al. Correlation for Z factor or for gas viscosity? I click this one, click viscosity. So the red one, the red line is actually from correlation, generated from correlation, but the black line is actually from data, laboratory data, the real or actual data. And you can see they actually don't match, but it's because we only have 2 points, that side and that side. We don't know what happened in real data, what happened here in this interval. Okay, so we can accept that it's okay. The matching is okay. All right. Especially because at this point, they are actually matched, right? At the same point. Okay, undo zoom. And also at this point. Okay. But we don't know in real life what happened in 3000 psi, 3400 psi, and other pressures. Okay, but Lee et al. Can forecast it, can estimate it, and the estimation is actually this red line. Okay, and we can also plot for Carr et al. Gas viscosity. You can see they are very close. But based on the parameter 1, parameter 2, and standard deviation, we saw that Lee et al. Is better than Carr et al. Okay. All right. So we are done for gas viscosity. What about gas formation volume factor? Okay, this is okay. Yeah, we only have one option for gas formation volume factor and Z factor. Both Lee et al. And Carr et al. Will give the same results. Okay, and let's check the laboratory data. Click it first. Gas formation volume factor, click. They don't match, unfortunately, but this is the best that we can do. Okay, we only have 2 points, but we cannot use this line in our simulation. So yeah, we will use correlation. At the end of the day, we will prefer the correlation because it includes wider range of pressure. In actual data, we only have 2 points, all right? But for correlation, we can cover, yeah, many parameters or many pressures, a lot of pressure, I mean. Okay. And that's what happened also for Z factor. This is from correlation, but in real data, the Z factor is like this. Okay. That's why in your laboratory data, it is better, it is best if you include several points. All right. So you can see the real trend. Minimum 3 points, I think. Not in our case, only 2 points. Okay. But yeah, that's what happened in day-to-day job, right? Sometimes we just need to take it, and from it we need to do whatever best that we can do in our simulation. Okay, so we can close, click done, click done. Yeah, you can see we will use matching. Okay, because we have done the matching. But you can see for gas viscosity, the best correlation is actually Lee et al. That's why I select Lee et al. Okay. And I also want to model water vapor. Okay. To make it more realistic. All right. And then I can click done. Or maybe you can check again, calculate match parameters. plot after I tick the water vapor, what happened? We can check. All right, this is the laboratory data. This is the Lee et al. Yeah, no significant change, no change actually in the matching. Okay, so click done. All right, so this is our PVT data and the selected correlation that will be used in our simulation. So we will use Lee et al. To calculate or to estimate the gas viscosity in 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 the wide range of our pressure. Okay, click done. All right, now we need to go to input. We need to input tank data. Okay, tank data. You can see the tank type is gas reservoir, and I will call it tank 1. The temperature is at 166 with initial reservoir pressure of 5,300 psig, and the porosity is 15% or 0.15 in fraction. And then for the Connaught water saturation is 25% or 0.25. For water compressibility, I will use correlation. And let's say I already know the original gas in place. Okay, based on static calculation or based on other calculations that are reliable, I know that my in place, my original gas in place is 2000 billion standard cubic feet. And I want to start the production from January 1st, 2008. All right, you can check validate, okay, and then click next. Now we need to input the water influx model. Let's say I already know the model for my aquifer, and I know that, yeah, and I know I have aquifer in this gas reservoir. And let's say I have done the analysis and I know that to best match the aquifer performance, I should select this one. And the system is radial aquifer. And let's say I already know the reservoir thickness is 120 in feet. Reservoir radius, let's say I already know 5,000 feet with outer inner radius ratio 5 and encroachment angle 100 degrees, 180 degrees with aquifer permeability 20 millidarcies. Okay. And then for the rock compressibility, let's say I know the exact number from my core data. I select user specified 3,5 e to the power of -6 per psi, right? The unit for, yeah, this one, rock compressibility. Okay, and then for the rock compaction, no need to input it. Let's keep it as default. And relative permeability data. Here we will use Cori functions to generate the rel-perm, the relative permeability. Hysteresis, no, in our case. And water sweep efficiency, let's assume 100%. And for this table, relative permeability to water, the residual saturation, 25%. You can see here, Connaught water saturation, right? And then for the gas relative permeability, the residual saturation 0.1, the endpoint 0.3 for water, and for gas 0.8. Okay, of course, higher than the water. The exponent 2,5, 1,5. Okay, you can click plot and you can plot removal first, the gas relative permeability, versus gas saturation, and also this one. Okay, the gas relative permeability versus water saturation, and also this one, relative permeability to water versus water saturation. Okay, so far so good. Let's say we haven't produced the reservoir. Okay, so I will not include production history. And because we don't have production history, we will not do history matching. No need for that. So we can click validate, click done. Okay, so you can see we have this tank reservoir, the red color, and the aquifer, the blue color. Again, I click, you can see we don't have production history. We haven't produced the reservoir. Okay, we still don't have any well right now. Click done. That's why we don't need to do history matching. These items will all be inactive. Okay, and now let's check the production prediction. Prediction setup, profile from production schedule. Yeah, we can select. Yeah, actually, we will not do the prediction or the forecasting using MBAL. The job will be done by GAP. Okay, later on, we will connect this model with GAP software. But yeah, we can select this one, prediction profile using well models, options use fractional flow models, right? Prediction start of production, and then user define prediction end will be ended at this date. Yeah, just to make it prepare for any simulation and for any forecasting, I will set up this production calculation setup like this one. Okay. And then for the production and constraints, I have these constraints, for example. So at 2 January 2005, the manifold pressure or the system pressure is 2000 psig. Yeah, the system pressure or the manifold pressure or the separator pressure or wellhead pressure, 2000 psig. Okay, basically they are different. Separator pressure is not manifold pressure. Manifold pressure is not wellhead pressure, but I think MBAL want to simplify that and they will call all the surface pressure as man pressure or manifold pressure. Okay, so it's not bottom hole pressure, it's not reservoir pressure, it's surface pressure. Okay, and let's say the constraint for gas rate maximum F 250 mm SCF per day or million standard cubic feet per day. And then at this date, at 2011, I will decrease the pressure, the system pressure, the surface pressure to extend the life of the reservoir. Okay, so far so good. And done. Okay, actually we can do the forecasting using this model, prediction setup, profile from product schedule, no wells. Okay, in this configuration, we don't install any well. So the forecasting will only done by the tank reservoir itself. Click done. Okay, and then for the reporting schedule, automatic. And then production constraints. Actually, I need to redo that. Or for example, using wall model again. Okay. But yeah, if you use Using well model, you need to connect it with well. So you need to prepare the well first. Okay. Yeah, actually, if we don't want to install any well in this model, we should select this one, profile from production schedule, but the production and constraints will change because we don't have well. We cannot consider the surface pressure. All right. That's why the only constraint is only date and the average gas pressure or gas rate. Okay. The average gas rate. We can keep it constant for several time, all right, for some time, and it will decline. You can do that actually. Let's do that. I want to take the date. For example, it will produce at this one, January 1st, 2008, right? 2008. And let's say the gas rate, 250 million standard cubic feet per day. Click done, reporting schedule automatic, and check the prediction. All right. You can see from 2008, January 1st, down to the end of prediction, which is January 2015. And you can click plot, check the prediction, the tank pressure. So the reservoir pressure will decrease from 5,300 down to this one, 3,038 here, the last point. And we can also check the gas rate. So from 2008 to 2015, we can maintain the production rate at 250 million standard cubic feet per day. What happens if I increase the production significantly to this one, 2,500 million standard cubic feet per day? Okay, or if it is too much, yeah, let's check just for example, right? For the case of example, you can see the reservoir pressure dropped to zero because the in place is only here, 2000 BSCF. So let's say I only want to produce at, yeah, this number. Let's predict what happened. Plot. Yeah, we can still keep the gas rate, but you can see the reservoir pressure reduces to a very small pressure, only 200, which is doesn't make sense. All right. Yes. So this is what happened if you simulate but without wells. Okay, you will get unrealistic results like this one because in reality the reduction of the pressure is too big. All right. Actually, we cannot produce at manifold or at surface pressure lower than 200, right? 215, if that matters. Okay, so yeah, you can do simulation like this, but it's not realistic. So again, we will go back to production profile using well models. Okay, and we will have production constraints like the earlier, but the well will be constructed using Prosper, and then we will connect the well and the reservoir using GET. Okay, we can actually connect the well using this software only. All right, this software alone can do that, but we want to connect it with network simulation. So better if we do integrated simulation. Okay, so I think we can call it a day. We have completed the reservoir discussion. We have created the reservoir model. So yeah, from here we will go to the next section, which is about well simulation or well modeling using software. And later on in the later section, we will connect the MBAL model, the reservoir model, with well model, the Prosper model, with network model, which is gap software. All right. So let's continue.